0.5 molar of hypochlorous acid. So that is a weak acid. So what we are doing here is dissociation of a weak acid. So the first step, we have to write the balanced dissociation reaction for hypochlorous acid. So we have HClO aqueous plus H2O liquid, and this is a reversible reaction. So we have the products. So hypochlorous acid is going to lose a proton, which is H. It's going to donate a proton, H to H2O, so that we will have 3 hydrogens now. So we're going to have H3O plus aqueous, and then now we're going to be left with ClO minus aqueous. So another thing, we have to write the Ka expression for this reaction. So we have Ka is equal to the product of the product of the concentration of the product, like, yeah, something like that. So we have H3O, multiply that by the concentration of that one, and then divide that by the concentration of hypochlorous acid. So we have HClO, and all of that is equal to, can just say is equal to 2.9 times 10 to the power of -8. Now the next step is to draw the reaction table. So we're going to go ahead and draw that now, and there's the table. So what we have to do now is to input the values that we have and find the equilibrium concentrations. So the initial concentration that we have is 0.5. So we're going to put that in. So we have 0.5 for hypochlorous acid, and then we exclude water, and then for hydronium ion we have 0, and for that one also we have 0, and then the change here is going to be minus x, and then here nothing, so here is positive x, and also here positive x. So in equilibrium we're gonna have 0.5 minus x, nothing there, and here we're gonna have x, and here we're gonna have x. So now we're going to find out what x is using that Ka expression. So we're going to say Ka is equal to the product of those products. So we're going to have x, multiply that by x, divided by 0.5 minus x, which is the concentration of the equilibrium concentration of hypochlorous acid. So we can rewrite this as the Ka expression that we had is 2.9 times 10 to the power of -8. So we have 2.9 times 10 to the power of -8 is equal to x squared divided by 0.5 minus x. So what we can do from here is to multiply both sides by 0.5 minus x, and we get something like this: 14.5 times 10 to the power of negative 9 minus 2.9 times 10 to the power of negative 8. X is equal to x squared. We can take that x to the other side, or we can take all of this to the other side, and we get 0 is equal to x squared plus 2.9 times 10 to the power of negative 8 x minus 14.5 times 10 to the power of negative 9. So you can plug this into your calculator and get the value for x. So the x value that we get is x is equal to 1.2, multiply that by 10 to the power of negative 4, and the is given in, that is the concentration, because this is x is the equilibrium concentration for hydronium ion, and that thing over there. So now that we have the equilibrium concentration, we have to find the percentage dissociation. To find the percentage dissociation, we're going to have to use this equilibrium concentration for hypochlorous acid. So we're going to say the percentage dissociation is equal to the equilibrium concentration for hypochlorous acid, which is 0.5 minus x divided by the initial concentration, which is 0.5. So we're going to multiply this by 100, and then we get 0.5 minus 1.2 times 10 to the power of negative 4, divided that by 0.5, multiply that by 100, and this should give you something like, so we get 99.976%. So this is not really possible. So we're going to have to assume that the equilibrium concentration for hypochlorous acid is somewhat equal to this value over here. So we're going to say, so let me do this. This solution is incorrect, so we're going to have to assume that 0.5 minus x, let me write it here. So we're going to assume that 0.5 minus x is equal to that value over there, and then we're going to find the percentage dissociation. So let me do this. Is equal to this value, 1.2 multiplied by 10 to the power of negative 4, divided that by 0.5, multiply that by 100, and now we should have 0.024%. Now this one makes a lot of sense. This one did not really make a lot of sense because we are dealing with a weak acid. And remember that weak acids dissociate partially. And that will be your final answer.